Hi. Can you guys see the screen and both see me as well as see the notes?
Yeah.
Okay, let's wait for 2 more minutes. Let's a few more people come and then I'll start at 9:38. Yeah. That's it. Okay, so we will be starting on, well, so welcome to Toolkit. So sort of Piyush has finished his module of teaching. So I will take over possibly for the next 14 lectures. I will go on and we'll do several modules in this. The first module which we will do is on the multiplicative weight update method. By the way, those of you who can turn on their screens, it would be good to turn on so that I have sort of a feedback mechanism. If you can, if it's feasible for you to turn on your video screens, please do turn it on. It will be helpful for me to just see people while I'm teaching, while I'm seeing faces. Okay, good. Okay, so how many participants do we have? We have got 9 participants. Okay, so we'll start a new topic called the multiplicative weight update method. We'll actually be spending quite some time on it. We'll be spending about 4 to 5 lectures on just this topic. So what is this? So let's actually get started off with, it's trying to solve a very basic problem in online computing. So think of it as you have it's an online problem, so you have to make a decision. So you have to make decisions at several time steps. So let's take a basic example of the following example, in which So you're looking at how a particular stock is behaving in the market. You want to know whether it's going to go, the price is going to go up or the price is going to go down, and based on this, you're going to either buy or sell the stock. So every single day, the stock is either going to go up or go down, and you need to buy or sell. This is one such thing that would happen. Other thing is you are betting on some game. There's IPL going on. There's a match happening every single day, and you're going to bet. You need to bet whether who is going to win. So there's a binary outcome. It's going to be this way or that way. You need to bet. Or there's the English Premier League going on, and there's a football match going on. And if you are like me, in which you have no clue about stocks in cricket or football, what I would do is I would like to, but I still want to participate in this. I want to trade in stocks. I want to bet on this. I turn on the TV to look at various experts giving their comments on it. And I want to then, based on these experts, take a decision, appropriate decision. So there are n experts, say there are n experts, at least 2 experts. Each of them is stating. So in the case of stock, one, the expert is saying the stock price is going to go up, the stock price is going to go down. In the case of the matches, in the case of IPL, each expert is saying this team is going to win, Mumbai Indians is going to win, Chennai Super Kings is going to win. So there's something about this going on. So they tell you a potential outcome. So, and for simplicity now, let's keep it a binary outcome. They're going to do this. So n experts are telling you something. Each one is giving you a binary outcome. And based on that, you are going to decide which of the outcome you are going to pick up. That's the outcome you pick up. And then the action actually happens. The match gets played. The stock, at the end of the day, the stock price either goes up or down. And then you realize which of the experts were correct, whether your action was correct or not. You get to see this all at the end of the day. So at the beginning of the day, you have to make a decision based on the expert's prediction. You make a decision. This decision could be either deterministic, randomized, or whatever. You come up with something, and then you decide what to do this, and then nature takes over and the game gets played. The stock price goes up or down, and then you look at the action, the result, and you observe the action. That is, you observe whether The stock has whether your action has resulted in a reward or a loss. Now, based on this, fine, that's the end of the, you gain a loss or reward, but you also get to know a confidence measure based on this and all the experts, because some of the experts got it correct, some of. Now, the same thing repeats the next day. Once again, you want to know whether the stock price goes up or down. The N experts predicting something, you need to take an action and you go ahead with it, and you keep doing this over time, over a period of, say, a horizon of capital T days. And we want to find out how well can we do this. Of course, you could say, I'll abandon the experts and I will take my best decision. But right now we want to say, I don't know how to take the decision. I have to choose one of the decisions of the N experts. It's a Boolean thing. So we'll assume all the possible outcomes are there among the N experts. We need to play according to one of the experts. Question is, how do we play this so that we minimize our total loss? This is going to be the basic. And so it's a basic framework in online algorithms. And what we will see today is we will see one very, very abstract way of handling this called the multiplicative weight update method. It provides us a sort of strategy to answer this. So I'll make things formal as time goes. We'll start with some baby cases, make it formal, and go as the class progresses. Hopefully by the end of this lecture or the early part of next lecture, we'll actually state the full algorithm, what I mean by this multiplicative weight update method. And just for a little bit of this one, it's called the multiplicative update method in the computer science literature, but this has been discovered and rediscovered several times independently across different disciplines. So it's been the core of several algorithms which were so in the machine learning community. There are these very basic algorithms called AdaBoost, Winnow, which basically are a version of multiplicative weight update method. In optimization, the optimization community, you want to solve LPs, linear programming, and they had also come up with using this multiplicative weight update method to do this, the optimization community. The TCS community had, the algorithms community had come up with this also to give faster algorithms. It's a different take on the optimization, faster algorithms for LPs, SDPs. In the complexity community, this was thrown by Impagliazio in the proof of the hardcore set lemma. This is something which we already saw last time. In the game theory community, this has been seen. This has been discovered when you try to understand in the computation of the value of zero-sum games. So we saw zero-sum games. Piyush introduced these. And then given a zero-sum game, you might want to compute its value. And when they were in game theory, when people studied it, they actually discovered the multiple. So this algorithm in its various guises has been discovered repeatedly over time. We'll see one particular abstraction of this over the next few lectures, and we'll see some of the applications to it. In particular, we will see applications to solving LPs, solving faster LPs and DPs. We'll see the application to the hardcore set lemma. We'll also see an application to, we saw the zero-sum game. This one, we'll see the approximating zero-sum game. And we also saw LP duality earlier on in the course. And we'll see a constructive version of LP duality. I'll state what that means, and we'll actually do all of this as applications of the multiplicative weight update method over the next lectures. And just for references, I will be primarily following, I'll put this up on the web page as well as on the Academy, this one, I'll be following a survey by Aurora, Hazan, and Kale. This is by now has become a standard survey for this multiplicative idea. So that's one thing. But we'll also be following a couple of lecture notes by Anupam Gupta and Ryan O'Donnell. And Wazirani, and so this is a lecture notes from CMU, and Wazirani and Rao from Berkeley. Okay, so that's all this. Let's start off with the baby case. By the way, this is going to be a new setting, this one, so feel free to stop and ask me questions repeatedly. We want to convey the idea to you, because I'm going to describe it in a very abstract setting, and then we'll go to concrete problems from next lecture onwards. And I will try to see actually if I can show you code running for this. So let's look at the warm-up case, in which there's one infallible expert. What do I mean by that? There is, among the experts, you do not know who, but there's one of them who is always correct. You don't know who it is. So let's work with this. That is, in general, in the case of stocks, in the case of prediction of games, there might be no expert who is correct. But let's start with the basic thing in which there is one expert that is correct. You don't know who this expert is. You look at the actions and you're going to play with them. Now, suppose this were the case, how would you? So let's state it. So then let's assume there are n experts. The number of experts will always use number n, and each of them give predictions. And for now, for this part of it, let's assume that these are Boolean valued. So it's 0, 1. Basically, they are saying the stock price goes up, down. It's a win-loss sort of prediction that they are giving. It's a Boolean prediction. Each expert is giving you a Boolean value. There are n experts, and you know one of them is correct. And what do you want to do? You look at the n experts, make an action. Based on, decide which is your action, which is the action you're going to take. And then actually, based on it, the stock price might now be adversarially decide your action and then correspondingly decide to go behave. Suppose you do a particular thing, it might do exactly the opposite thing. The stock price gets to know, the game knows that this is how people have bet for a particular this one, and people might try to fix the match based on the betting. So we're going to assume that is, you look at it, you make a strategy, all of this is public knowledge, and then the actual action happens. And then you observe which of the experts have got it correct, which of the experts have not got it correct, and your own action, whether it has got correct or not. And what the goal is to minimize the number of losses. Okay. So what is the strategy that would you follow? In this case, let's walk the baby case in which you know that there's one expert who answers perfectly. You do not know who this expert is. And so in this case, how would you try to, what's the candidate algorithm that you can come up with?
So maybe every time when the experts are, so in the beginning, maybe you can just, I don't know, go with a majority or something arbitrary. And then once you know the results, you know who all were wrong. So if they were wrong, certainly you can eliminate them. They are not like none of them are infallible. So maybe then you keep repeating this every time, and eventually you go converge towards the infallible expert.
Yeah, so exactly. This is this one. So in this case, what you'll do, you'll initialize. Just going to be a little more. So this way for t equals 1 to capital T, you will initialize you'll first initialize your set of experts to be all of these guys. So E is the set of all experts which up to now have not made mistakes. Set of experts who haven't yet committed error. then that's the initialization. This is just the base, whatever Varun said is what, for t equals 1 to t, you're going to act according to the majority prediction of experts in E. Observe the outcome. Eliminate from E all experts with an incorrect prediction. So that's the basic algorithm we're going to be working with. Is the algorithm clear? I've just written in elaborate English whatever Varun said. So how many mistakes will you make? So let's assume T is a very large number. T keeps on going. It's like the stock price. I'm going to keep doing this investing day after day after day. And T is a very, very large number. N is a small number. N is not too large. There are like 10 experts, 12 experts, or 5 experts of this form. How many, what's the maximum number of mistakes? What's the minimum, what's the, sorry, minimize, what's the maximum number of mistakes I could make in this?
Number of experts.
Is it the number of experts? So each time I get it wrong, because we have acted according to the majority, half of the experts in E have got it wrong. So each time you get it wrong, half the experts in the set E have got it wrong and they are eliminated. And you will never eliminate the infallible expert because the infallible expert is going to get it correct every single time. So the set E never becomes empty. But each time you make a mistake, it reduces by a factor of half. It reduces by a factor of 2. How many times can this happen? This can happen only log n times. So the analysis for this, the following simple thing, that is each time. So I'm going to use the word I for, there are the experts and I'm going to make the decision based on the experts. I'm going to use throughout this, the action of the algorithm to be I. So I'm going to say, each time I make a mistake, half the experts in E are eliminated. So this is the first observation, are eliminated. E is always non-empty. As it contains the infallible expert. Hence, number of mistakes I make is strictly smaller than log 2. Okay. So irrespective of how much the time horizon goes, T can be a large number. So eventually you'll see after log 2n, you are correct. You have found out who is the infallible expert, or you're possibly it so happens that there are some other experts who manage to get it correct. They are not infallible, but at least for these decisions, they've all got it correct. So the game proceeds, and but you make only at most log n errors, log n mistakes in this full. Is this clear? This is a warm-up case. Is it okay? So that's what I want to say. In this case, we have the number of mistakes is at most log. So please stop me and ask questions. Now we'll move on to the next, the general case, in which we have imperfect experts. Okay. So they might or might not be any expert who's going to get it correct all the time. They are all giving their prediction. But now the question is, you want to do something. You want to you're going to make some actions based on their predictions. Now, what do you compare yourself against? This is you're going to make some actions. You want to compare. There are multiple things you can compare yourself against. So one is you can compare yourself. You can come. So we will in all the things we want to make the minimum number of mistakes. But you want to compare the minimum number of mistakes to somebody else. So of course you could compare the minimum. So at every time step there is a best action. Among the n experts, at every time step there is one of the actions is better than the other actions. And so you might want to choose this trajectory. This is possibly the best trajectory that you want to choose. You could compare. This is one thing you could compare against. This is the best. At every time step, you find out who is the best expert that gives you, and then look at the. So what I want to say is minimize. So compare the algorithms perform. You want to compare the algorithms performance against what? So the one option is the min. Sorry, one option is the sum. So let me set up some notation before starting this. So we're going to assume that at every time step, what you have is the following. That is, at every time step, you have. I'm going to come up with this number MIT. And what is MIT? MIT is, so I is an expert and T is the time. And MIT is a number, belongs to 0, 1. It's 1 if expert I gets it wrong. So it's possible, it's the loss vector. Gets it wrong, and 0 otherwise. So at every time step, you get this vector. At the end of the game, you get this vector MT, which is M1T, M2T, MNT. This is at the end of, so they make a prediction. At the end of the day, you see their actions. That there's a loss. This one, it's a Boolean vector. You can see a bunch of 0 1s. So one thing you could compare yourself against, the first thing you could compare against yourself is summation I going from 1 to T. Sorry, T going from 1 to T, minimum over I in N, MIT. That is, for every time step, you find the guy who makes the least error and work with this. This is one thing you can work with. The other one is you want to compare yourself with the best fixed expert at the end of you. So you do not know the time horizon. You let them go. You want to compare yourself against min I in N, T equals 1 to T, MIT. Here you're fixing one expert and you're asking how I want to do as well as the best expert over the entire period of time. And this is every time step you can change which expert is going to work, compare it against. What we will see is these are two possible things you can compare your outcome against. And what we see, because of the online setting, the first is more or less too hard to fight against. And I will not do this in class, but I will possibly make this into a problem set. It's an easy thing to show that this one is not. It's very basically, if you're going to compare yourself against this measure, the number of mistakes, there's an additive difference between this and me, which is at least the number of time steps. I want to say this is more or less infeasible to compare against. That is, I can come up with schemes. There'll be at least an omega t additive difference in between the errors any algorithm can make versus if I compare against this. So what we will actually work is with this notion, that is the best expert with hindsight. And what we want to do is make the number of mistakes to be not something which looks like omega t. T is the maximum. T is the number of mistakes you can make, because if you're going to make a mistake at every center, that's the number of mistakes. We want to make this much smaller number than t. Simply, we want to make it like little o t. That will be the goal, and the goal will be to make it as small as possible. And we'll show that if against this you can do certain things. If this is the measure of comparison, you can do it as well as the best expert with hindsight, and that will be the goal in our problems. Okay. Okay. So this will be our measure. Notice in the infallible expert, both these are the same measure, because there's one expert who's going to get it correct all the time. In the case of infallible experts, the reason we had to come up with this is because there is no infallible expert here. Therefore, there might be not one good guy, or the best guy might be making errors, might be making mistakes at various single time steps, at various points of time. All you want to do is compare yourself against the best expert with the knowledge of hindsight. But you don't get to do this. You have to make an online decision every single time. The decisions you make are irrevocable. You have already, based on the predictions of the expert, you have bought or sold the stock. You have to bet so much money at the end of every game. For this one, you have those decisions are irrevocable. But you are going to compare the performance of your algorithm, your strategy, against the best expert who's being predicting across in the entire time horizon. Okay. So what would you do? In this case, what would you do? How would can we modify the previous algorithm to this setting?
I think I've sort of seen something like this before. So
let me say, there are a few natural things to do. What are potential approaches?
you can keep some kind of like confidence over these experts, right? And then
before that, let's take out the basic things. Act according to the majority. There's one option, but this is a bad option, because it might be that the majority of the experts actually get it wrong. There might actually be one expert that gets it correct all the time, but the majority of the experts always get it wrong. So you can't be acting according to the majority. You need to sort of penalize people who have got it wrong. So what you could then do is, because you care about a large time horizon, you could observe initially how a few experts behave, find out who are the good experts, and then act only according to those good experts. So figure out who is a good expert in the first few rounds. And then act according to that expert. But once again, here I never made any assumptions that there is a good expert. That is, there is a good expert according to this notion, but that expert need not work well in the beginning. Like, for example, we've been through this pandemic for a while. There have been multiple models who are predicting how this one is going. Initially, to start off with, there were some models which worked well, but you stick to them, and over time you realize that almost all models sort of floundered in this one. So you can't just go by this notion will take. This is our comparison metric. If you go by this, it's not clear that the best guy according to this metric actually works well in the beginning. They might not work well in the beginning. They might actually begin working only in the latter stages. So we don't want to do this. So what we'll do is a mixture of both. That is, we will put a confidence measure. That is, we will not, unlike the previous guys, because nobody is infallible, we will not eliminate we will not eliminate an expert when they get it wrong. What we'll just do is lower our confidence on that expert. And then instead of taking majority, so we'll start off with putting equal weights on all the experts. then take the majority of them, this one, look at the action. Then you know which of the experts got it correct, which of the experts got it wrong. Then we'll reweigh our confidence level in all of them. So that, and we lower all those, instead of eliminating them, getting the confidence level to 0 as we did in the infallible expert, we will just sort of lower it by some fraction and then ask, and then now we have a new set of weights. And now we'll take the weighted majority at every single step and do the same. It's just a modification of the previous algorithm in which we just eliminated all experts who got it wrong. What we'll now just do is just lower our confidence. We'll just lower their weights. Instead of making the weight go from 1 to 0, we'll reduce it from say 1 to half. Each time they get it wrong, we'll reduce it, we'll halve their weight. And then take weighted majority according to this. And let's see how this works. So this is what I'm going to call. So the proposed algorithm is going to be same as the infallible. Case, except lower weight of experts.
Then what is the motivation behind not removing these experts which are not correct?
Because you don't know that there is no the best. So we want to compare ourselves to this particular expert, the expert who gets it, who makes the least number of mistakes over time. It might be that the initial cases they actually got it wrong. So if you throw them away, you have thrown this expert out of your set itself. You want to keep them in. So when they begin getting it correct, you want to actually begin working according to them.
And that infallible.
In the infallible case,
expert is always right.
In the infallible case, we always knew there is one expert that is correct all the time. And hence we could do this. Hence we could eliminate. Once you know somebody got it wrong, you know that there is another guy who's going to get it correct. So you can drop this guy. There was another guy who performed at least as good as this person. Therefore, you could drop it. But now you don't know this. In the case that experts both perform, the experts are imperfect. They could kind of give right answers, wrong answers. There's nobody who's going to give you the right answer all the time. So if you eliminate a person who just because he gave you the wrong answer, now it might be that so far he gave you the wrong answer, they gave you the wrong answer, but from then onwards, they're going to actually begin giving you the right predictions. So you don't want to eliminate them. You will lower their weight, but once you realize that they are performing well, you want to ensure that they are back in the game. Okay? Lower weight expert instead of making it 0.
So how do these experts make decisions? Like, do they follow some probability distribution, Bernoulli or something?
So we are not, by the way, so that's what this algorithm, we are not going to assume anything on how the experts could do whatever they want to do it. The experts could do whatever you want, and then when nature acts to decide to make the action, it could observe all the n experts prediction, it could observe how you are acting based on the n experts prediction and act based on that. It could do it. So we are working in a very, very general setting. I'm writing a meta algorithm in this setting. When we go to specific examples in which we are following linear programming or approximating the zero-sum game or looking at low LP duality, in each of those cases, we will instantiate how exactly the experts are acting. And right now, I'm talking it in a way. So the reason this algorithm is so universal is because it makes absolutely no assumptions on how the n experts are. N experts, well, some of them could be just plain astrologers who are just making random guesses. Some of them could be actually making well-formed decisions. Some of them are just playing adversarially against you. I'm not going to make I'm not going to make any assumption of the experts. What I want to do is I want to perform as well as the best expert in hindsight. Okay. So let's just do stop me and go fairly slow. Just make sure that we have the model correctly, because we're going to instantiate this model over the next few lectures in several different settings. We'll have one meta algorithm that I'll do today, and then this or today at the beginning of next lecture, and we'll instantiate this for various other settings. Good so far? Okay, so now let's write down the weighted majority algorithm. It's going to be I'll call WM for short. So as before, there will be an initialization phase in which for each expert, I in N, you initialize their weight at time step 1 to be 1. So you start off with the equal weights for all the experts. That's the initialization step. Then, as time progresses for time steps 1 to T, make a decision based on the weighted majority of experts' predictions using the weights, using the weight vector WT, which is W1T, W2T, Wn. So I will be using small letters for the scalars and capital letters for the corresponding vector quantities. I can't do bold-faced like we would do on this one, so I will use capitals and smalls. I somehow don't like putting those lines above, so we'll do this. So you make a decision based on it. So this A, and then B. You observe the action. Observe the action. And then C, you update the weights of all experts who predicted wrongly. What's the update we'll do? We will sort of say Wi T plus 1. So into half. I'm just going to lower their weight. Okay. So is the algorithm clear?
Yes.
It's the same algorithm. It's almost the same algorithm as before, except that we didn't make the weight 0. We just made the weight half of before. So we are lowering their confidence. So the point is, initially when they made bad choices, possibly this one is lowered, but over time, and let me highlight this differently because that's the main highlight, the weighted majority rule. Remember to?
Oh, Prahlad.
Yeah.
So immediately I can see just a couple of small variants. Like, so you chose to half the weight.
Yes.
We could have been possibly a bit more like if instead of half, it's some delta.
So we will see that's something which we will see right away. In 5 minutes, you will see that whether half is a good choice or something else is a good choice. We'll see that.
And also one more thing, like here, when someone goes wrong, we are decreasing the weight. Will it ever help to increase the weight when someone does right?
Because we are taking weighted majority, it is the same thing. No, if you just penalize the guys who got, because it's actually Boolean decisions. Just penalizing them who got it wrong is the same as rewarding somebody who got it correct.
Yeah, makes sense.
So I'm just going to do one direction. We will see various this ones. This ones right now there's just a 0-1 thing. So this is what we will do. And in fact, we'll see both of these. Hopefully, by the end of today's lecture itself, we will see how to do it. So I want to analyze. So is the algorithm clear once again? I want to analyze how well does this perform, and how well does it perform? How well does it perform against the best expert with hindsight? This is what we want to do. So let's set up some notation before we state our theorem. So
is an application of this the TCP congestion control algorithm as well? where we do multiplicative decrease on a loss and additive increase on a on correct transmission?
So yeah, so these are all variants of this. I don't know exactly what the algorithm is. So there have been various algorithms. This notion of how you penalize an expert who got it wrongly and how you reward an expert who got it correctly. There have been various ways of doing this. You are suggesting a way in which it's multiplicative for the people who got it wrong and additive for the people who got it right. There are multiple things. I'm talking about just the multiplicative weight update.
So just
This is one big meta algorithm which we'll analyze, and later on we will see there have been previously ways in which you do an additive, you change the weights additively. Right now I'm going to be just talking about multiplicative modification, multiplicative update of the weights.
So the TCP thing is somewhat qualitatively different. There is just two parties there. There are just two parties. There are no experts. You just back off exponentially. So if the channel is quite,
okay.
You don't try. So basically, if you try to communicate and if you fail, then you wait twice as long. Basically, but if you get a clearance, then you don't start doubling your rate. You only increase it slowly. So yes, so it's similar. So it's similar. It is in this idea of like multiplicatively changing your sort of response, but it's somewhat qualitatively different from this.
Yeah. So just recall. So what did it? What did I want to write this? This is not what I wanted to write. So we had previously defined MIT is the indicator vector whether expert I made mistake at time t. And let's call NIT to be basically sum of MIT, t going from 1 to so MIS, yes going from 1 to t. So up to time t, the number of response, and I want to compare this against n of t, which is the number of mistakes made by the weighted majority algorithm till time t. And the thing we will see is after t steps.
So NIT should be summation WIT MIT.
No, right? It's just the number of which one?
This NIT.
No, this is just, I'm focusing on one particular expert and asking what is the number of mistakes made by that expert.
Okay. And then what?
And this is the number of mistakes made by the algorithm totally.
Okay.
And what we want to compare is, we want to compare this against the minimum of these. Okay? And what we will show, that is after t steps, for every expert I, NT actually performs so it's no more than 2.4 times the number of errors made by any expert, in particular the best expert, and another additive log n factor of log 2.4 log n. So in particular, the above holds even with respect to the best expert I star, which is org min I of NIT. Okay. So let's okay, this is the magic in these proofs is basically all of these proofs will go via a potential function argument. So once you realize what's a potential function, these proofs are actually extremely simple. It's very easy to write this down. Why do you use this potential function? This comes out naturally in various things. In fact, when we see the next algorithm in a modification, the potential function, in fact, is written in the algorithm itself. But we'll come up with a choice of potential function that actually makes this very clear. So what's the potential function I'm going to use? I'm just going to use the following potential function, phi t. Which is defined to be just the summation of weights at that particular point. So just the summation of the weights. So what do we have some initial this ones about them? We know that phi1. What is phi1?
This is number of experts.
So it's n. Now each time Wm makes a mistake, what happens? How does this potential change? Each time Wm makes a mistake, what's going to happen? Why does the algorithm make a mistake? Because majority is predicting wrongly. That means at least half of the experts' weights, according to this weighted majority, is going to reduce by a factor of half, according to this weights. So in particular, each time the algorithm makes a mistake, what you have is phi of t plus 1 is less than or equal to phi of t. So half of them possibly remain unchanged, and half of them drop by a factor of half. Strictly more than half, at least half of them drop by a factor of half. So in other words, each time a mistake is made, this happens. Each time a mistake is made, this potential function drops by a factor of 3/4. Each time the algorithm makes a mistake, the weighted majority algorithm makes a mistake, the potential drops this one. Therefore, phi of after the entire thing, what is this going to be? This is going to be less than phi of 1 times 3/4 times the number of mistakes. So the algorithm performs NT mistake. Each time it gets a mistake, this is falling by a factor of 3/4. So at the end of t steps, phi of t plus 1 has at least shrunk by a factor 3/4 to the power nt. But on the other hand, phi of t plus 1 is certainly greater than wi of t plus 1. It's equal to the sum of all of them. It's greater than this wi of t plus 1. And how does wi of t plus 1 compare against its original value? In fact, this is exactly wi of 1 into half to the power ni of t. Each time it gets it wrong, its weight drops by a factor of half. So the original weight, and this is how it progresses. Is this clear? These are both upper and lower bounds on this potential function. On one hand, each time the algorithm performs wrongly, you know half the experts, according to this weights, half the experts according to this weight, their weights are going to reduce by a factor of half. Therefore, this potential function reduces by a factor of 3/4 each time the algorithm gets it wrong. For each individual expert, their weight falls by 1 each time they get it wrong. So at the end of the time horizon, phi t plus 1 is at most phi of 1, which is n times 3/4 to the power n of t. And it's at least wi of 1, which is just half to the power ni of t. Now you just put them together. Half to the power ni of t is less than or equal to n times 3/4 to the power of nt. Okay. Take logarithms, and what do you get? You get log 4/3 into nt minus log n is less than ni of t. I'm taking log with respect to 2. So for nt is less than or equal to nit plus log n by log 4/3, and that 4/3 is that funny number 2.4 that we had over there. This is approximately 2.4 times. Questions so far? Notice the algorithm made absolutely no assumptions. Hari's question: how do the experts behave? I don't care how the experts behave. No matter how you behave, it guarantees to me that I will not make any more mistakes than 2.4 times the best experts, plus this additive factor of 2.4 log n. And the proof is very clear. Once you lay your hands on this potential function, the proof is actually trivial. Okay. So now let's go back to, so can I, the one thing which I would like to ask is, this is not a nice number, this 2.4 over here. What I would like to do is I want to compare it against NIT. I don't want to get a multiplicative loss of 2.4. Can I reduce this 2.4 to close to 1? And can I get rid of this additive factor? So these are two places where it's bad. One, it has this multiplicative loss over here, and then it has an extra additive loss. Try to look at for both. Let's first focus on the multiplicative thing. I want to compare and get this done. And answer to this will be the first thing, which this one, we'll actually change half. We'll change half to, we won't drastically reduce the weights from 1 to half. We'll just reduce it from 1 to say 1 minus eta. That is right. Make the weights. So we'll actually talk of it with a, I'm going to bring, so let me actually use a different color. So I'm going to modify this. There's going to be a parameter eta. So I'll call this weighted. This eta is some number between 0 and half. And what we will do in this world is into 1 minus eta. So question which I was asking is two questions. Is the multiplicative loss of 2.4 avoidable? 2, is the additive loss of order log n avoidable? So we'll first address 1. For that, we will modify Wm to Wm eta, which is basically the weight function going from okay. And let's just go and stare back into the proof. So let's look at the modified proof. So analysis of Wm eta. So we're going to do this. Let's just repeat the same thing again. Phi t plus phi t at any point is going to be defined to be summation wit I in n. So we initially phi1 was 1 as before. Each time wm eta commits a mistake, phi t plus 1 is less than phi t. So what is it going to be now? So half of it will remain possibly plus 1. The other half, what happens? It reduces by a factor 1 minus eta. Therefore, this is falling by phi t is, it falls by a factor 1 minus eta by 2, not 3/4. Eta being half was the case which we were looking at. It falls by this factor. Therefore, hence, at time t, phi t plus 1 is less than or equal to phi 1 into 1 minus eta by 2 and this is the number of mistakes made by that. Each time the algorithm makes a mistake, this falls by this factor. Therefore, this is this. On the other hand, phi t plus 1 is greater than or equal to wit t plus 1, which is what? Which is exactly wit into 1 minus eta to the power ni of t. So you do the same thing again. So wi t plus 1 minus eta nit is less than or equal to n times 1 minus eta by 2 n of t. So once again, how do I write this? So n of t into, now let me write it with respect to, so minus ln 1 minus eta by 2 minus ln n is less than or equal to ni of t minus ln 1 minus eta. So in particular, nt is less than or equal to nit into ln 1 minus eta by ln 1 minus eta by 2 plus ln n by minus ln n 1 minus eta by 2. And the whole point of doing this was previously we had ln of half by ln of 3/4. We want this ratio to be as close to 1 as possible. The 2.4 basically came because this was ln half and this was ln 3/4, and that gave you the 2.4. Now, if you choose eta to be small enough, these both look the same. This is going to become a number close to 1. Eta. So you don't reduce the weights. You don't reduce the weights from 1 to half. You sort of reduce from 1 to 1.9. That is, the weight goes from 1 to 1 minus eta. If you keep eta small enough, this number will not be sorry, something I have got this. Hopefully this number you can keep it close to 1. We will not, hopefully this number will reduce it. I would like to make it as close to 1 as possible. We will not, see, we won't get it to 1. So here I want to make some, I don't want to have the lns picture. So I'm going to use these approximations for ln 1 of x. Ln 1 of x is always greater than or equal to x. And minus ln 1 minus x is always less than or equal to x plus x square if x is in 0 half. So this, if I use these approximations, I get that ni of t is the numerator. I will use this expression. I'll get eta plus eta square. The denominator, I will use the other one. I'll get eta by 2. This is ln n. I have an eta by 2 here. Sorry, my n's and etas look very close. Hopefully, you can distinguish it with the tail. I didn't think of this when coming up with a notation. So this is 2 into 1 plus eta nit plus ln 2 ln eta. So I just want to state the same. Let's copy this here. What we have here is 2 into 1 plus eta plus 2 ln. This is okay.
So then this gives us this kind of trade-off between the additive and the multiplicative.
It gives you a trade-off between the additive and the multiplicative. This one. So I can get the multiplicative, but notice I still haven't got the multiplicative to 1. But I can get the multiplicative to as close to 2 as possible. But that comes at a cost of the additive. The additive becomes larger and larger. This one. We will address this. Later on, we will see that actually this is unavoidable. You will have to pay an additive loss. We'll come to that few lectures from now. But for now, I want to more, for the current, this one, I want to more focus on the multiplicative loss. This says I can get the multiplicative loss to 2 into 1 plus eta. By the way, is the statement for the weighted majority. The weighted majority algorithm is an extremely simple algorithm. And already it tells you that I can perform as well as the best expert in hindsight. That seems to be a very surprising fact. I am doing something very online at this point, and I'm comparing myself against an expert who works well with the benefit of hindsight. And yet this algorithm works as good, almost as good. There's a multiplicative cost of 2. Let's ignore the 2 ln over eta. I'm hoping that that's not a large number, because I'm talking about time horizon capital T or something. This is a small one. I want to say this is a small quantity. This is not too bad. I already got this. We'll focus on trying to see if I can reduce this 2 further to 1. But any questions so far?
I have a question.
Sure.
So the updation only happens when we make a bad decision, right?
Yes.
So there is another possibility, like even if we make a good decision, there will be some experts which make bad decisions.
Yes.
So we can penalize them, like
no, we are penalizing.
We are not doing that.
We are penalizing them. The algorithm is penalizing them. The algorithm, if you recall, the algorithm is penalizing. Update the weights of all experts who predicted wrongly. Each time an expert got it wrongly, you are penalizing them. I do not know how to use that in the analysis, because when I got it wrongly, it might be the case that it's because the weighted majority was actually a perfect weight. It gave the weight 1. Everybody got. I don't know how to exploit that fact.
Yeah, right.
The algorithm is doing it, but I don't know how to use it in the analysis. So far, so good.
No, I mean, wait. It's not like that. We do need to update the weight every time someone makes a mistake, right? Or do we only need to update it when we make a mistake?
No. So I won't be able to write this fact. I won't be able to.
When you're using NIT in the
NIT, I don't know. I want to penalize them whenever they make a mistake, and it seems right to penalize them whenever they make a mistake. You just penalize. They got it wrong. They might not have been the majority, but you just want to drop them off. Suppose there's a guy who consistently is wrong. Their weight has to eventually go down to keep on decreasing. There's no point keeping them in the game if they're going to get it consistently wrong. Okay.
Also, this login thing. So you said that later we'll see this is unavoidable. Is it going to be just some adversarial thing that you can do?
So we will basically show that we will give a no matter which algorithm, forget about multiplicative weight, no matter which algorithm you give, I will give you a way to make actions at every step. In fact, actions will be it's not even going to be adversarial. It's the probabilistic method. You just act in a random fashion. You can show that you will have to, I can come up with a way in which, there's a way in which nature can act at the end of every step, such that you will have to pay this additive loss because you're doing this in an online fashion. Okay. Yeah, let's stick to this log n. There's an interesting question. We'll stick to that later. Right now, I want to focus on the 2, on the multiplicative factor. And something I want to observe is actually, let's look at the following setting. There are just 2 experts, A and B. And the way it works is this way. You have to choose one, and they always give differing answers. It so happens that they always give differing answers. So you decide to choose, say, expert. At the first step, you do not know which one to choose. You just arbitrarily choose expert A. Then I make the right action to be B to be the right expert there. Weighted majority is now going to make the weight towards B. In the next step, I'm going to make A to be the right guy. You're going to flip it again. Weighted majority will flip it again. You go, and if you notice this at every single step, so each time, if the algorithm predicts this person, the action, the nature is going to work adversarially and choose the other, this one. So the algorithm ensures the nature is sort of acting adversarially such that you make a mistake at every single time step. It ensures that the action, it puts the right action on the expert who's not the weighted majority. Which is not, you're just 2 experts. You put the action on that one. So you are going to, the number of mistakes you are going to make is actually capital T. The algorithm is going to make capital T, this one. Notice that both the experts are going to make T by 2 mistakes, because I'm basically going to keep flipping between them. So when I compare them against, this algorithm, and there's no way I can get around this. This algorithm, this is the best expert, they make only T by 2 mistakes, whereas the algorithm is making T mistakes. So this is a case in which 2 is unavoidable. 2 is unavoidable for the algorithm, but actually you can show that this is not just a phenomenon of this algorithm. Any algorithm which is deterministic, deterministically taking an action, nature can adversarially decide to work against it and ensure that you can never get a trade-off better than 2. The same example which I gave, counter example which I gave to show that you can't do 2, you can't do better than 2. You can actually do it, not just work against the weighted majority algorithm, but against any algorithm, as long as the algorithm is deterministic. It's exactly the same argument. You have to write it down a little more carefully. I will try to make this into the next problem set. I'll try to push it into the next problem set so that you can word this properly. So just against any deterministic decision maker, it will show that you cannot avoid a factor of 2 against the best expert's mistakes. If the algorithm is going to make deterministic decisions, this factor of 2 is unavoidable. So the questions which we are going to ask is multiplicative factor of 2 unavoidable? And the answer says yes, if algorithm is deterministic. Not 1 plus eta. Yes, 2 is I want to say 2 is unavoidable. If the algorithm is deterministic. And not just for weighted majority eta, but any deterministic. the argument I say tells you the weighted majority can't do better than a factor of 2, but you can turn this argument, write it more carefully, and show that any algorithm can't do better than a factor of 2. Good. So this sort of says I need to do something. If I work with deterministic algorithms, I can't do anything. So now I'll choose how to do. I'm going to give the algorithm the power to toss random coins. What does it mean, the power to toss random coins? The algorithm is going to use, so it's going to be almost the same algorithm. You're going to do these weighted majorities, but you're not going to act according to the weighted majority. You will toss a coin proportional to the weights. And you'll toss an n-sided coin or an n-sided die proportional to say probabilities are proportional to the weights, and act based on the outcome of that die. So you're going to each step, you're going to do it. But nature does not get to know the toss of your coin. The nature knows that this is the probability with which this is the probability distribution which you're acting. The nature does not, whoever is playing. So the way the online setting was is the experts make their predictions. Based on their predictions, you are allowed to come up with a strategy. So far, we came up with a deterministic strategy. You are going to now make a probabilistic strategy, a randomized strategy. You're going to put some weights on the experts. So you're going to toss some coins based on this. But the coin is not yet going to be tossed. You're going to say, this is the coin I'm going to toss with these probabilities. Then nature makes an action. The stock price either goes up or down. The cricket match is played. It's won or lost in this one. Now you look at what is your expected. The coin is tossed and you choose and you base your action. You look at your expected number of mistakes. You're not looking at a particular sequence of mistakes, but your expected number of mistakes. So nature can work adversarially only against your probabilistic strategy. Nature does not get to see the random coins that you are tossing at each step. Okay. So we're going to modify the weighted majority algorithm. Now we're going to give a randomized version of it, which is not going to take the weighted majority, but it's going to toss a coin and behave according. It's going to take an action based on the. They toss a coin toss an n-sided coin whose probabilities are proportional to the weights and act accordingly. Is that clear? And this is going to be our final algorithm, at least the final meta, this one. So I'm going to sort of generalize it far more. I'm not going to just assume Boolean inputs in this one. I'm going to assume that the answers are not just win-loss. Each expert's prediction has there's a cost factor associated with it, which is not just a win and loss. It's a real number ranging between -1 and 1. So what we will do is, so this is going to be what I will call. So get around the two factor, get around the two multiplicative factor using randomness. And that's going to be what we will call the multiplicative weight. Update method. So what we'll do, we have about 10 minutes left. So what I will do is we'll state the algorithm fully, this one, and we'll do the analysis of the algorithm in the next lecture. Okay. So I'm going to make, so the algorithm is going to be more general than before. More general in the sense that the win-loss or reward loss is no longer Boolean values. Previously, it was this. general in the following sense. Previously, we had each MIT was in 0, 1, but it's a Boolean value corresponding to win. 0 was win and loss was 1. That was how we did it. What we now do is each MIT is more general. It's some number between -1 and 1. We're going to allow this. That is, it's going to be a more general one. So it's the how much the prediction is wrong. If it's a positive number, that means that is the loss associated with it. If it's a negative number, the prediction actually is a sort of a reward. You're putting both of them into the picture. So I'll allow for non-Boolean rewards or losses. And so in general now, this vector MT that we have at this one is going to be this vector of M1T, M2T, MNT. It's some vector in -1 to the 1, N. This is at the end of each day, you get to see this vector. After the action has been played, you get to see every expert, what is their reward and loss. You get to see this at the end of each game. At the end of the day, you get to see this. At the end of each time step, you get to see this. And we are going to act with, say, we're going to have probabilities. We're going to come up with probabilities, P1T, P2T, how PNT. This is what I'll call the probability vector PT, where each PIT is the probability with which algorithm acts according to expert I at time t. Okay. So now let's state the MW UM eta algorithms. As before, there's a parameter eta. Eta is a number in 0 to half. And by the way, so we are going to assume that the rewards are between -1 and 1. The rewards are bounded, and we'll see it in the analysis that the rewards are going to be, there's a bound on how much you can gain and how much they're not arbitrarily large or they are not arbitrarily large. If you want to say arbitrarily large, you have to scale everything, and you'll be penalized for this. We'll see it pop up in the analysis. We'll need to put a bound on how large the rewards or the losses are at any point of time. And this will become even more evident when we actually look at various examples. Okay, so what is the algorithm? So it should be by now quite clear what I'm going to do. So initialize this as before for all I in N. WI1 is going to be set to 1. That's the initial setting. Now we're going to work for time, each time step. For t going from 1 to t. That's it. Now you're going to choose time step. You choose the decision I according. Choose a decision I according to the probability distribution. PT, which is P1T, PNT, where what are the PTs by themselves? Each PT, PIT itself is just the normalized weights. It's weight divided by phi t, and phi t itself is just the sum of the weights.
Prahlad, so this, correct me if I'm, this is equivalent to doing the following, right? In just the weighted majority case, instead of just going with the weighted majority, what you're doing is assigning the majority decision of probability, which is like weight, normalized weight, and then the minority has the remaining weight, and then you're choosing this with just a two-sided coin. This would be
They were only Boolean things.
Boolean.
So you just had two coins. You just put this one and you chose a coin, and the adversarial argument worked primarily because both the numbers were very close to half, and you had to choose. So now the two of the numbers are very close to half. You might actually choose the minority opinion too,
right,
but it's going to be the same thing. So this is exactly the same thing. Several of these experts might be actually predicting the same action. So you will be actually doing it. So you can rewrite a new probability distribution based on what are the actions they are doing.
Right.
So I'm not going to talk about it. They're saying some action, and I'm going to act according to the nth expert with probability, the ith expert with probability PIT. It might be true that the ith expert and the jth expert are giving very similar this ones. I don't take this one. This is a far more general set work. I'm going to write it down in this language.
Prahlad?
Yeah.
So we can also think of this as like this portfolio kind of thing, right? That you invest your wealth according to this distribution. Then it is deterministic. You don't even have to.
Yeah. So the question is what are we trying to minimize? Are we trying to minimize? We will eventually only minimize the expected performance of the algorithm, which is exactly the portfolio. This one. We will look at, we won't say with high probability this algorithm works well or something. I won't be talking about this. I'll just talk about the expected number of mistakes made by this algorithm, in which case this can be stating that there are n experts who are saying buy and sell this stock and how the stock goes, and this is, you are redistributing your wealth based on the n stocks, and this is your expected way in which your wealth is going at each time step. We might look at this example later on. So I'll come to that when I state the main theorem. So it need not be a randomized algorithm. It need not be a randomized algorithm per se, but I'm going to still take action based on all the n experts. I'm not eliminating experts in the action. It's some expected value of over all the experts is what is the performance. The performance of the algorithm is some expectation over all the experts' actions, and this expectation is taken according to the probability distribution which I have defined right now.
Okay.
So you do this, then you observe the costs. Observe the cost, which is what? Which is you basically observe this vector mt, which is m1t, mnt. This is some vector in -1, 1, n. You observe the rewards and losses for all the n experts for what they have at this time step. And now you update the weights. And how am I going to update the weight? One minus. So you're going to make it, the update is going to be based on how much. So the closer MIT is to 1, you need to reduce their weight even more. If MIT is 0, you don't have to reduce their weight at all because it's 1. If MIT is -1, you actually want to increase the weight. So we'll do MIT times 8. This is how much the weights are going to increase and decrease. Okay. By the way, even to write this down, I needed MIT to be the numbers between -1 and 1. Otherwise, the weights might become negative numbers. Otherwise, this number might become negative. I need 1 minus. I need this quantity to be a positive number because the weights all have to be positive. If I have to talk about a probability distribution, I need this to be a positive quantity. And for that, I need MIT to be at most 1 at any point of time. It's not clear why it should be at least -1. We'll come to that later, but it should be at most 1 even at this point. And just you keep repeating this. So that is going to be the algorithm. I'm pretty out of time. What I will state is I will state the theorem we'll prove next time, and then we will prove the thing. And the idea is going to be, the proof is going to be very similar to the proof which we had already. I'll do this later. Okay. So once again, this is refers that first one. What we will talk about are two things. We're going to talk about the loss at a particular time step is going to be what? The loss at a particular time step of the algorithm. This is what I want to write. This loss of MW UM eta at time t. So notice that this is just going to be summation I in n MIT dot PIT. That's the expected loss, rather expected loss. This is the vector MT, the inner product of these two vectors, MT and PT. And furthermore, this is the loss at each time step, and L of t is the expected loss at the end of time t. So this is just summation L of S going from 1 to t. This is the expected loss. So what we want to compare is the expected loss of the algorithm against the loss of any expert. In fact, against the expert which incurs the least loss. And the theorem which we will prove, which will just, it's going to be more or less, the proof is going to be exactly what we proved. So assuming all costs MIT are in -1, 1, and eta is 0, half. We'll show that L of t. What is L of t? L of t, remember, is just t going from 1 to t, the inner product of MT against PT. This is less than or equal to the loss of any particular expert, I equals 1 to t, MIT. Take any expert, then for any I, for any expert I, plus eta times summation I going from 1 to t mod mi of t plus ln n with eta. Let's stare at this for a little while and then we'll conclude. This one. Let's work in the case of the MIT. Let's go back to our setting where the MITs were 0 or 1. In this case, what do you get? You get summation MIT plus an eta times summation MIT. So it's 1 plus eta. So this avoids a factor 2. So in particular, even if the MITs are all positive, you already get 1 plus eta times this number. So this already shows that you're good. By using this randomized strategy, we are shaving off that factor 2, both actually in the multiplicative loss over the best expert, as well as there was another 2 over here. Both of the things we have shaved off the factor 2. And the analysis is going to be almost identical to the analysis we have seen before, except we'll be working with this expected loss rather than because we are working with a randomized algorithm rather than deterministic algorithm. Any questions? So this is what we will prove next time. So the takeaway is the randomness gets rid of the factor of 2. Okay, I'll stop with this. Any questions? I will stop the share and